This brief video is to explain, from high-level perspective, existing open questions in connection to the Navier-Stokes equations for incompressible fluids. In addition to that, we will share new and exciting findings in that context. An important and still unresolved problem in fluid dynamics is the question of global regularity. This is Navier-Stokes equation for incompressible fluids. It describes, using language of mathematics, how fluid velocity, pressure, and forces acting on fluid change over space and over time. Incompressible fluids are used in this context as an approximation of real fluids, which can somewhat compress. Mathematical expression of incompressible fluids describes fluids as being fully incompressible. That approach simplifies equations compared to the ones which have to take compressibility of fluids into account. Simplified equations are easier to work with. However, mathematicians have good reasons for worry. In some scenarios, equations produce results which are not expected, and which are referred to as blowups. Such mathematical blowups is not something that mathematicians can expect to happen from any reliable equations. Therefore, they set a task to prove mathematically if such equations are reliable or not. However, task of proving it mathematically, one way or another, turned out to be much more difficult than anticipated. Thus far, it was not mathematically proven if incompressible Navier-Stokes equations can be considered fully reliable. On the other hand, it was also not known if there is a specific example such that incompressible Navier-Stokes equation does not have any solutions. In essence, question is, can it be mathematically proven that equations work well, or is there an example which demonstrates that equations do not have solutions? Any one of those two answers would represent progress in understanding fluid dynamics. In such scenario, mathematicians and physicists would be able to further evolve understanding of fluids and the ways to describe its behavior mathematically. Finally, one example of fluid velocity and external force vector fields with smooth characteristics is found. When both vector fields are applied in the Navier-Stokes equation, it does not have any solutions over Euclidean space at time t0. Once both examples of fluid velocity and external force vector fields are applied to the incompressible Navier-Stokes equations, equations produce three mutually different results for pressure. Of course, it is expected that incompressible Navier-Stokes equations have one solution for pressure. However, in this scenario, it results with three solutions, which is not acceptable. In addition to that, one of three solutions for pressure has one term, which at time t0, evaluates to zero division with zero. Such result is indeterminate. Obviously, solution for pressure that has term which is indeterminate does not represent a solution. What that really demonstrates is that it is possible to find an example of fluid velocity and external force for which equation does not work as expected. Such a result raises new questions, including, what is in the essence of such behavior of incompressible Navier-Stokes equations? Incompressibility is not yet observed with empirical evidence in the reality of nature. All physical objects, including fluids, are to some degree compressible. Regardless of how small such compressibility might be, it is unlimited number of times more compressible compared to the incompressible fluid, which, as per mathematical formulation, cannot compress at all. Therefore, a hypothesis worth exploring is that mathematical formulation of fluids incompressibility might be beyond boundaries of what can be considered as physically reasonable. Embodying mathematical formulation of incompressibility within equations describing fluid behavior in space over time might be abstraction which does not have a match in the reality of nature. In such scenario, mathematics representing laws of physics, like Navier-Stokes equation, together with mathematics without any match in the reality of nature, cannot be expected to result with physically reasonable outcomes, such as blow-ups. Therefore, a hypothesis that incompressibility of fluids condition might be at heart of the problem, and one worth exploring.
For more details and technical information, please follow links provided with this video. Your feedback is very much appreciated and valued. Thank you very much for your attention.